So the last question, question 9 actually, for your waves test, is all about two-source interference pattern. We've looked at this with lasers before. Here we've got some speakers playing sound and an oscilloscope or microphone attached to an oscilloscope, which measures the intensity of the sound. So where we're in the central first order maximum or zero order maximum, it will have a high amplitude reading in the oscilloscope for a loud sound, quite one at B, and then a loud one again at C. So this is our first order maximum. We're asked to talk a bit about the logistics, if you like, of the experiment. So first of all, we're asked to explain why it's difficult to locate position B, this first minimum, precisely. And really, if you think about it, that's to do with the fact that that's a little bit subjective. The position of the minimum reading will be quite broad as you move your microphone and the oscilloscope it's attached to from A through to B, then C. It will decrease gradually and then start to increase again, and then this is a fairly broad region. So actually, that broad region means it's hard to find a definitive position for the minimum. Similarly, we have issues with measurements of the distance between position A and the speakers. In terms of getting it down to the nearest sort of centimetre, these speakers, speakers when you see them quite large, what are we calling the central point of the speaker? Is it right in the middle? Is it we're measuring to either edge? Same with the microphone, are we measuring from the beginning to the edge? So one of the issues might be it's difficult to identify the exact centre of the speakers or even the microphone. The other issue, which lots of you identified, is that these big distances here, 3-4 metres, you're going to need a tape measure to measure those. One of the issues when using tape measures is that you get some lag, so again an accurate reading to centimetres may be a little bit unrealistic. For the last part of this question, we're asked to work out what the wavelength of the sound wave is. So we've got these two measurements here. We know this is the zero order maximum, this is the first order maximum, and that first order maximum, just like when we did lasers and light, we know that the path difference between the two sources is equal to a wavelength. So that's the logic that we're going to use here. Path difference is equal to one wavelength, and then we just need to find the difference between those two distances. So 4.17 metres take 3.56 metres, 0.61 metres for the wavelength of the sound. For B part 2, we're asked to kind of discuss the implications of maybe taking that distance measurement between the speakers and the microphone with a laser, so being able to measure that distance more accurately, and what the implications of that, in particular what the implications for the percentage error and the value we pull out for the wavelength. So obviously, using a laser is better than using a tape measure. So we're going to decrease the percentage uncertainty in that distance measurement. But then we've got to think about actually what's the issue? What is the thing that's affecting this percentage error in the calculated wavelength? And it isn't actually the taking of the measurement. It's the identification of the position of those maximum and minimas. We talked about that at the first part of this question. And also the fact that the speakers are broad, so picking the point to measure to is an issue. So even if we can measure it really accurately, because we can't identify the point very well, then actually it's going to have a limited effect on the overall uncertainty of the experiment. So the issue, like I say, is with the subjective position of the microphone at the broad maxima. Using a laser doesn't address this, and so we're going to have actually not much change in the percentage error on the calculated wavelength. Just because you're refining your measuring technique, if you're uncertain for whatever reason, because it's not very clear what you're measuring to, then you're not improving the uncertainty. You can only measure as good as the thing you can identify. We're then asked to find the speed of sound using the information that we've got. The frequency of the sound emitted was 560 plus or minus 30 Hertz, and we're told that the uncertainties in the distance from each speaker to position C is plus or minus 0.02 metres. So first off, define the speed of sound using our 0.61 metre wavelength and 560 Hertz, so frequency times wavelength, and we get a little bit over 340. So 340 Hertz to two significant figures. My data is to two significant figures. So I've got that bit, and then we can think about the uncertainty. So there's two ways of doing this. You could find like the maximum possible value, if you like. Use 590 and then whatever the maximum wavelength is, multiply them together, and then work out what the difference is between your top value and 340. I'm going to do this with percentage uncertainties. So I know that because V is equal to F lambda, the percentage uncertainty in the wave speed is equal to the percentage uncertainty in the frequency plus the percentage uncertainty in the wavelength. Now, if we're going to think about the uncertainty in the wavelength, we're told that the uncertainty, the absolute uncertainty in the position of the speakers and point C is 0.02 meters. So that's not the uncertainty in the wavelength, it's the uncertainty in the speaker distance. And we have two speaker distances, so from speaker 1 and speaker 2 to point C, that potentially have that uncertainty, which gives us an overall uncertainty of 0.04 meters. Think about it. We may be 0.02 meters too large for one measurement and 0.02 meters too small for the other measurement, which is going to give us a value for the wavelength of 0.04 off our 0.61 meters. So our percentage uncertainty in our wavelength is our 0.04 divided by 0.61 times 100, and that gives us 6.5%. Our percentage uncertainty in our frequency is 30 over 560 times 100, so that gives us about 5.4%. If we're going to add those uncertainties together to find the overall percentage uncertainty, we get about 11.9%. And then if we work it through, 11.9% of 340 is 40.5. So it's 340 plus or minus 40 meters per second. Note how I'm consistent with the number of decimal places I'm giving my uncertainty to in response to in relation to my stated value. If you only had this 0.02 meters, you get about plus or minus 30. You get 3 out of the 4 marks. Okay, finally we're told the student reverses the connections to speaker 2 but keeps connections to speaker 1 unchanged, and explain what the effect would be on positions A and C. Well, where before A and C were maxima because the two waves are meeting in phase, if one of the microphones is now in antiphase with the other, the two waves are going to be meeting in antiphase. And as they're going to be meeting in antiphase, then we would expect a destructive superposition, a minimum in the amplitude of the signal or the volume of the sound.